Hello again, Statisticians. I am back. I apologize for the break in the middle of this video if you're watching it all the way through at once. But last night it was getting cold and dark, and I was losing my voice, and to a certain extent I was losing my mind and saying things I didn't want to say, so I just stopped recording, and I'm picking it back up now with the 2 to Tango slide. So one of the ways I was losing my mind that I want to fix is this issue of whether we're drawing a graph with 2 population distributions or 2 sampling distributions. And I realized, I'll just show you what the graph's going to look like. It's down here on this slide. There are 2 distributions. They're normally distributed. And I've labeled them both as sampling distributions because that's kind of the part that matters. I realized that in my old hand-drawn notes, when I was like scribbling things on the board all the time, I would draw both the population distribution and the sampling distribution, and that's where the confusion came in because I was doing both. But on this slide, I'm only going to do one because, like I said, I'm not that graphically sophisticated with a computer, unfortunately. So we're just going to roll with it as it is. But basically what we have here are going to be 2 sampling distributions. One is going to show us our hypothesized mean, and the other is going to show us the actual population mean, which is not the same thing. So both of these populations will generate distinct sampling distributions with different means. And then we're going to be focusing for the moment on the type of errors, or where we find the errors in this setup. So alpha, which is our proportion of type 1 errors, will be the proportion of the sampling distribution for the hypothesized mean that falls to the right of the criterion line. There's going to be a lot of words in this slide, but I'll show you the picture on the next slide, and hopefully it will make a little more sense when you see that. And then beta, or the proportion of type 2 errors, will be the proportion of the sampling distribution for the actual mean that falls to the left of the criterion line. So I guess the other crucial part of this that I need to say is that the actual mean is not just different from the hypothesized mean, but it's greater than the hypothesized mean, which is why its entire distribution is shifted over to the right on the graph, which would be, I guess, in this direction for you if you're watching this video. Okay, I'm not going to talk about the picture anymore. I'm going to show you the picture. I always tell my students to show rather than tell in their presentations, and that's what I'm going to do now because it solves a lot of problems. So here's what this setup looks like. We've got these 2 sampling distributions, and the hypothesized distribution has this mean of 0, which we've seen before. Excuse me, and it's the standard normal distribution, so it has a standard deviation of 1, and we're calling that the standard error because we're just pretending that this is a sampling distribution. And then we also have what I'm calling the actual sampling distribution here, which I've tried to sketch out in purple. Hopefully you can see that. And if you can't see it on the curve of the distribution itself, maybe you can see it in this lovely arrow I've drawn here, linking up the actual sampling distribution to the curve. And that mean is going to have, or that distribution is going to have a mean of 3. So it's not dramatically different from the hypothesis, but it is a little bit different. And you can think of a realistic setup for this. Say we're looking at like the VOT of unaspirated stops in some language like English, and we just guess, well, maybe the mean's going to be 0. But in reality, it's not quite 0 because there's maybe a little bit of aspiration or a little bit of time between the release burst and the beginning of voicing. So we actually get a mean of 3 when we actually look at the entire population. But that's a subtle difference, so how can we actually tell whether the hypothesis is wrong or not? So basically, an important point here is we're going to set up a criterion for making that judgment. And the criterion will be set up entirely based on what our hypothesis is. It's not set up based on what the actual sampling distribution is because we don't know what that is. We're just making a guess that our mean is going to be 0. And then on the basis of that and what we see from the standard deviation of our sample, we put the criterion here. And then basically everything on the right side of this red line, if we get a mean on that right side of the red line, we're going to reject the null hypothesis. And if we get a mean for a sample mean on the left side of our criterion line, then we're going to accept the null hypothesis. And in certain cases, we're going to make mistakes, right? So just on the basis of our assumption, we'll say, well, we know that sometimes even with this mean of 0, we're going to get sample means over here on the right side of this criterion. We're going to get those means 5% of the time. We know that just as a fact, even if this were the real sampling distribution mean, we'd still get some sample means over here, and we're just going to accept the fact that we make mistakes of that nature 5% of the time. What we don't know off the bat, just because of our setup is how many beta type mistakes we're going to be making, beta being this part of the actual distribution on the left side of the criterion. So I've got these labels down here on the bottom as well, just to try to make this clear. But again, on the left side of this criterion, we're accepting the null hypothesis. And on the right side, we're rejecting the null hypothesis. And I'm saying, well, in reality, we have this purple distribution, which is the real distribution for whatever data variable we're looking at here. And even if the mean is actually 3 for this variable, say it's VOT or what have you, sometimes we'll get sample means over here on the left side of this criterion, which, because of our presumptions, we think just kind of verifies or at least doesn't reject the null hypothesis. So we may get a mean variable value of like 0.5 or something like that, or maybe 0, whatever. In that case, we would accept the null hypothesis, but that could happen even if the actual mean is 3. Okay, this is what it looks like. We've talked about the various testing paradigm outputs at great length in many different permutations through the multiple lectures that I've produced for this series. But this is what we're looking at for the time being to try to understand power. Okay, so we'll come back to this graph again in different sort of incarnations as we go. But as we try to figure out what it's saying to us, I want to ask you a few questions. And normally I ask these in class. In this case, I'm going to pause a little bit after I ask them so you can think about them for a touch. But I'll lead into them with a few comments first. So what we're trying to find out is how likely we are to recognize that our sample mean comes from a sampling distribution which is different from the hypothesized sampling distribution. And as I've said before, just a minute or two ago, I'm going to simplify this a bit by making it not just different from the hypothesized mean, but greater than the mean. So if we do have a mean that's greater to some extent from our hypothesis, our hypothesized mean, how likely are we going to be to actually find out that that's the truth? So that's kind of the big question that we're trying to answer here by doing power analysis. And the tricky part of answering that question is that the amount of the actual distribution that will lead to type 2 errors, beta % of the time, is actually dependent on where we set the alpha criterion for the hypothesized distribution. So it's not strictly about the reality of the situation here. It's not all about what this purple distribution is doing in terms of either its mean or its standard deviation. It's about this relationship, again, between our hypothesis and the actual mean and what sort of sample mean we get out of this whole setup, right? So we put this hypothesis wherever we want to, and we just happen to put it at 0, which in this case might be a reasonable place to put it, might not, who knows. But it's close enough to 3 that it might make this a little bit tricky, actually finding out that we're wrong about the 0 hypothesis. All right, I hope I don't lose my voice again, but if it does, I hope it's comedic for you. Anyways, so it depends, answering this question depends on where we put that hypothesized mean, and it also depends on how far apart the two means are in reality. And another thing it's going to depend on is how many observations are in the sample, the n number that I talked about before, which is going to affect the standard deviation of the sampling distributions. So I want to walk through what effects these things can have on our power analysis, again, by asking you a few questions, which I hope you at least try to answer in your mind before you find out what I think the answer is as I walk through these slides. Okay, so here's our power picture again, and we've seen all these different proportions of our various distributions on either side of the criterion. So we've got 2 parts of each, and remember that we're either accepting the null hypothesis on the left side of the criterion or we're rejecting the null hypothesis on the right side of the criterion. So that determines what happens to the 2 portions of each distribution. But the important part that we're looking at now is one we haven't thought about before. It's not a mistake that we're making. It's not either a type 1 error or a type 2 error. It's instead a correct rejection. What is the proportion of correct rejections, or the power of our analysis, which we've symbolized before as 1 minus beta? It's the amount of the actual distribution to the right of the alpha criterion. So the actual distribution is this purple one over here, and the proportion that we care about, or that we're trying to quantify in doing power analysis, is this bit over here on the right-hand side of the criterion. So this is 1 minus beta, that's power. It's this part of the actual distribution. all of it to the right-hand side of the red line. And then the beta part of it is the proportion of type 2 errors we make. That's on this left-hand side of the criterion line. But basically what this is saying, again, we just run one experiment. We get one sample. We calculate a mean on the basis of that sample, from that sample data. And that puts us somewhere here on this x-axis, right? It just gives us a number. And then we're kind of imagining all this stuff behind the scenes going on. But ultimately, if we're on this right-hand side of the red line, we're going to reject the null hypothesis and say, oh, there's a purple distribution out there somewhere that we hadn't thought of before. And if we wind up on the left-hand side of this red line, then we say, nope, it's just this hypothesized mean. We're going to stick with it. We'll say it's 0. Even if it's not exactly 0, we can't prove ourselves wrong, so we might as well go with it. Okay, that's all we're getting here is just one number, the mean, and then we're trying to interpret on the basis of these distributions, like how often are we likely to get that significant effect where we reject the null hypothesis, where we wind up on the right-hand side of this line. Okay, crucial point to remember is that alpha, which are these type 1 errors, and 1 minus beta, which is the proportion of correct rejections we get, those two proportions are both going to be on the same side of the criterion. They're both over here on the right-hand side. Okay, so we make an inference if we're over here, if we wind up with a sample mean on this side, we make an inference to reject the null hypothesis, but we don't know ultimately if we're making a false alarm error or if we're making a correct rejection. We just make that decision and go with it, and then, whatever. Reality will hopefully sort itself out in the end, but we won't necessarily ever know, as usual. So, yeah, what are we talking about here? So let's think through this conceptually and then walk through the power calculations for a specific example. So as we try to make sense of this, keep in mind that this is kind of a practical discussion. It's not just conceptual. So one of the practical parts of this is that both alpha and n, the number of items in our sample, are factors that we can control when we run the analysis for our experiment. So we could change those two parameters if we want to. Normally you don't change alpha, although you could. But there's a conventional value for that. But n is a big issue. Like when you're running your experiment, you're like, how many items should I get in my sample? How many subjects should I run in my experiment? I want to know how much work I need to do to reasonably possibly get a significant effect out of this study. Okay, so these questions are at play as we roll through the analysis of our experiment and also this attempt to understand what power means. Okay, so we might change alpha. But if we do, what effect would changing that alpha criterion have on the power of the analysis? Drink break. Pause. That was refreshing. Okay, what we get out of changing alpha is that if alpha goes up, then power will go up as well. And I think I said this before, but alpha and power are both on the same side of that criterion line. So if we move that such that alpha goes up, then 1 minus beta is going to go up as well. And when I say go up, I mean the proportions of type 1 errors and the proportion of correct rejections we make are both going to go up quantitatively. And basically that means the more false alarms we're willing to accept, the more significant effects we're going to capture as well. Okay, so you got to make some mistakes to kind of capture what you want to capture in your data if it's there. Another way to put it is that the more false alarms we accept, the fewer significant effects we're going to miss. And so, yeah, you can think about power as the proportion of significant effects that you actually get. You can also think it in the reverse way. You're going to reduce the number of misses you get, that proportion of the purple distribution on the left-hand side of that red line. And then as you might imagine, the flip side, the exact opposite is true. So if you're reducing the number of false alarms, if alpha goes down, then power goes down as well. And remember, we can set alpha to be whatever number we want it to be. So if you just set alpha to be like 0.10 rather than 0.05, then all of a sudden your power goes up. But if you reduce alpha to like 0.01, then power goes down as well. It's a lot harder to capture a significant effect in that sort of setup. So the fewer false alarms we're willing to accept, the more significant effects we're going to miss. Right. So that's just part of the game. We'll take a look at what this means in the graphical form here. So I've got all of our little parts of the distributions laid out here as we've seen before. And basically what we're talking about is shifting this criterion one way or another on this x-axis. So if we push it to the left, and normally, again, I do this on the board, but hopefully you can imagine this whole red line is going to move in this direction over here towards the hypothesized mean. And what will happen is this little bit of the black distribution, the alpha part, will get bigger because the red line will cross at higher and higher intervals of this normal curve, and thereby leave more of the distribution on this side. And the same thing is true of what happens to the purple distribution. So this red line is moving over. We're cutting off the purple line at lower and lower spots. So more and more of it is going to be on the right-hand side of the distribution. These are mistakes down here. These are false alarms. These are correct rejections. We're getting more of both of these guys. And then if we do the opposite, if we move it to the right, we get less of both of those alternatives, right? So that would decrease the number of false alarms. If we shifted the red line way out here to like 0.01 or wherever, we'd get very few false alarms, but we get far fewer significant effects as well. And I guess at this point, I don't know how deeply you thought about answering that question when I asked it, but oftentimes at this point in class, I will get a question like, well, why don't we just set it to sort of be at the optimal point where we're getting the fewest number of errors possible, which would be kind of right in the middle of where these two distribution lines cross each other. And all I have to say about that is that sounds great. Of course, we want to make the fewest number of errors possible, but the fact is we don't know exactly where this point is because we don't know exactly where the actual sample or distribution mean happens to be. This is something we're trying to find out on the basis of running the experiment. And in fact, we will probably not ever find out exactly where that mean is. We're just always making guesses, unfortunately, and shots in the dark. And that's why we have hypothesized means to begin with, I guess I could say. So if you thought of that question, good. I want you to do as well as you possibly can with your data in life, but sometimes it's just not possible to get everything you want, and that's kind of the story of statistics, unfortunately. Okay, so here's another question. Having answered that one or two questions before, what effect would changing the sample size have on the power of the analysis? So like I said, this is something else that you can tinker around with when you're setting up your experiment, is to change that n. You can make it bigger or smaller, however you want, however many subjects you want to run in your study. We're going to keep alpha constant. We'll just keep it at 0.05 for now because that's almost always what we normally do. But to answer this question, what you'd have to do is to think in terms of your standard error estimate, which we define as the standard deviation of the sample divided by the square root of n. So that's where n comes into play here. And hopefully you can think, if you just think through this mathematically, if we're going to increase n, the bottom part of this fraction is going to become bigger, even though we're taking the square root of it. So the whole thing would decrease, right? So the bigger n is, the smaller our standard error becomes. And another way to think about that in a more positive light is that the bigger n becomes, the more accurate our estimate of the mean becomes as well. That's what I mean by standard error decreasing, I guess you could say. Graphically, what we're going to see if we increase n is that the sampling distributions will become narrower. They're going to get squeezed towards the middle. So I'm going to try to give you a couple of graphs to show you how that would work. I'm going to start up my engine again, and it's going to beep. But I got to stay warm here because a frozen professor is not any good to you. Anyways, here's what we started off with, the same setup we've seen before. Both of these sampling distributions have standard error 1, or that's their standard deviation. I'm not going to get into specifics of like n numbers, but just say, well, what happens if we increase this, if we increase n to the point where the standard error now becomes 0.8? And this is subtle, but I'll flip back and forth between these two graphs, and hopefully that will help you see what's going on here. But in the standard error equals 0.8 situation, these curves have become narrower. Both of them have become narrower. And for now, we're just assuming they both have the same standard deviation, just to make it simple. But what that does is that it gives us less overlap here on the bottom. So I was just talking before about, well, why don't we set the criterion to a spot where, we have the optimal, number of mistakes, which is the fewest number of mistakes. That would be right where these two cross over. If we increase our n or decrease our standard deviations of these distributions, that crossover point is going to be lower overall. So there's less sort of overlap between the two, which means we're just going to have less errors overall. And in fact, as I do this is a subtle point, but to make sure that there's still about 0.05 or 5% of the distribution on the right-hand side, 5% of this hypothesized distribution on the right-hand side of the criterion. When I make the standard errors smaller here, I got to move this red line over a little bit to the left so that there's still 0.05 or 5% of this distribution over here on the right-hand side. If I kept it where it was, there would be hardly anything over there. There would be less than 0.05, but that's, like I said, we're trying to keep alpha constant. So that's one of the things that happens, is that this criterion is going to shift over to the left, and therefore more of the purple distribution will be over on the right-hand side, right? For two reasons, right? Because if we just kept the criterion where it was before and we just squeezed the purple distribution, made it skinnier, then more of it would be on the right-hand side of the criterion anyways. But we're also having to shift that criterion a little bit over to the left, so we're getting even less of the purple distribution on that side. So we're getting a lot fewer beta errors over here, and we're increasing our power considerably, and power being 1 minus beta, or the proportion of the distribution over here on the right-hand side. So this seems to be a good thing. We're making less mistakes, or we're making fewer mistakes, not by trying to figure out where the optimal point of setting the criterion is, but just by running more subjects, getting more data, and that gives us more accurate estimates of what these means are. So 1 minus beta in this case will include a bigger part of the actual distribution. I'm going to show you one other setup, which would happen if we went the opposite way. So let's say we ran fewer subjects, we got fewer items in our data sample, and that gave us a bigger standard error, or a standard error of 1.2, and that's going to make these distributions fatter than they were before. So we can see that hopefully pretty clearly going between the skinnier standard errors and the fatter standard errors here. These are the 1.2s. And so to keep this setup fair, I need to have 5% of my hypothesized distribution over in this little squidgen. And to do that, I'm going to have to move the red line over pretty far to the right, because there's more overlap now between the two distributions. And to capture just 5% of this guy, I have to move the red line further out than it was before. You can see it's past 2 in this case. Before it was less than 2 for both of the smaller standard deviations. And what that also means is that there's going to be less of the purple distribution over to the right-hand side of this criterion. We are taking off a big chunk now on the left-hand side. These are all the type 2 errors I'm going to make. These are all the misses I'm going to make. And what's left for power is considerably less than what we saw before. So fewer subjects, fewer items in your sample, power will go down. More subjects, more items, then power will go up. That's a pretty clear relationship between those two. I will make another subtle point here as well. But I want you to note that not only can n change the standard error or the standard deviation of those sampling distributions, but the standard deviation of the sample can too. So if we go way back, here, I said our standard error estimate is the standard deviation of the sample divided by the square root of n. And this is, changing n is straightforward. You just say, well, I'm going to run 30 subjects rather than 20. And then so all of a sudden n gets bigger, and you have to do more work to do it, but whatever. You just run the study again. Changing standard deviation is not, you can't set, I'm going to make my standard deviation 45 as opposed to 23 or something, right? That depends on the data you actually get, but you can kind of try to cheat the odds in your favor a little bit with that. If you are really desperate and trying to get a significant effect for whatever reason. But you could do certain things with your experiment to sort of reduce the variance in the data that you collect, right? So you could perhaps get a more homogeneous sample of data from wherever and say, well, I'm only going to study like male speakers in their 20s, and I'm not going to take female speakers, or I'm not going to take a wider range of people than that. I'm just going to target a smaller population, I guess. And then for that reason, I'd expect the standard deviation to go down. Or maybe they're only from a specific place, or have a specific language background or something like that. You could try to tweak your standard deviation in that way to try to reduce that overall error estimate and thereby increase power. So just to keep in mind, if your standard deviation is large, or the larger your standard deviation is, then power will go down because that will have the opposite effect of running more subjects. But if your standard deviation is small, then power will go up, right? So if your standard deviation is small, you're making those curves skinnier. They're getting further and further apart from each other. It's easier to distinguish sort of a different actual mean from your hypothesized mean. This is, I guess I would say, borderline cheating. If you remember the story of Daryl Bem and his ESP experiments, this is the sort of thing that's, he might have thought about doing if he was really trying to sort of cheat the system to prove his point. Again, I don't know all the details on that, so I can't say one way or another that he was doing that, but it's sort of within the rules of the game, but not really within the spirit of the game. And that can cause some problems in terms of trying to figure out actually what's going on in reality. If you're trying to sort of just change your perspective on the data just to get a significant effect, you're not really doing science there. So be careful with that. But I want to let you know that that possibility is out there, because not necessarily so that you will do it yourself, but because other people might, I guess, is one way to put it. And if you're ever reviewing papers, you might keep a lookout for that sort of thing. All right, so deep thought question number 3. What about the mean of the actual sampling distribution? What effect does it have on power if it is further away from the hypothesized mean? And what effect does it have if it's closer? Let's think about this for a second. And maybe let's go back to those graphs so we can kind of visualize it. But what I'm saying here is, throughout all these graphs that I've shown you, I've always had the hypothesized mean at 0, the actual mean at 3, but maybe the actual mean is over here at 4, or maybe it's over here at 2. What difference would that make on the amount of power we get out of this setup? And hopefully you can see that fairly straightforwardly. But if the hypothesized and actual means are further away from each other, more of the actual sampling distribution will fall to the right of the alpha criterion, so power will go up, right? What we're looking at graphically is how much of the purple distribution is over here. And if the mean is over here, then more of that purple distribution will be over here too, so my power is going to go up. And the opposite, gives you the opposite effect. So if the whole distribution shifts over here, then less of this purple distribution is on the right-hand side. And I get less power out of my setup, right? So hopefully that's fairly clear, but these are all things that can factor into the amount of power you get. And so I've said both these things about how power goes up and power goes down. But kind of one of the morals of this story is that, number one, reality matters, which is the important thing because we're doing science. And like I said before, we're trying to figure out what the reality of the situation is. But kind of unfortunately, the accuracy of your initial hypothesis will matter in this respect too, right? So before we were playing around with a situation where we hypothesized that the mean of this distribution is at 0 based on whatever reason, right? But we could have guessed, well, maybe it's at 1. And then this entire black distribution shifts over here to the right. And then these two distributions are closer to each other. So simply by making sort of a more accurate guess about where the actual mean is, we get less power in that case. So let's say the actual mean is actually 3, and we guess that it's 1. We're less likely, if we run an experiment gathering data of this sort, we're less likely in that case to get a significant effect. And we might still sort of accept the fact that our mean is at 0. We might accept that our mean is at 1. In that case, we might accept that hypothesis because it's just harder to disprove it if the actual mean is closer to the hypothesized mean. So it's a little bit funny. We're getting at a point where reality matters, but we don't really ever find out what the reality is. We just kind of get a reasonable guess about whether our hypothesis is true or not. So it ultimately winds up being a game of like what that depends to a certain extent on our hypothesis as much as it depends on the reality of the situation too. And like I said, it's a bit unfortunate that we were playing a guessing game and then it gets a little messy in that respect. But this is sort of the underlying sort of vision of how we can calculate what power is. So I just wanted to walk you through this in detail so that it makes sense. And again, I'm sorry for the pause in the middle of the video. I know it's probably a long video as it is. I'm going to stop talking about the concept of it in the next video, but I'm going to pause before I make that as well. And in the next steps, we will look at how to calculate power specifically using R and some actual examples from students' research that I've collaborated with. And we're also going to talk about something called effect size, which is basically a measure of how distant or distinct these two means will be, the hypothesized mean and the actual mean. So stay tuned for that. And I'm going to stop talking now because I have talked enough.